Okay, so let's build a divide by 2 counter, divide by 2 circuit. So this is a 74 LS74, a very, very popular chip. It is a D flip-flop, D latching flip-flop, and the way that it works is on rising edges of the clock, it latches the value of D into Q. So we've been using these as our latches. We're instead of using a 7474, we're using a 74 LS374 or 574, which are octal versions of this, but the 74 versions are the two. The way that we're going to use this is, am I in the frame here? Let's move it over. We are going to have the Q and the not Q, and we have the D, and usually there's a little arrow here, chevron to denote where the clock comes in. So if you hook not Q to D, and this is your incoming clock, so this is a rising edge, then the value of Q is always going to be not Q, so it's going to toggle. So the first time, let's say Q is 0, not Q is 1. So if you clock this, then this 1 gets into D, and then the 0 becomes a 1. Then this becomes a 0, and anyway, it goes round and round and around. So divides by 2. So what we're going to do here is there's also a clear and a preset, which are not clear and not preset. So we need to tie this one high, and we need to tie the preset high, and the D is going to connect to the not Q, so we need to wire these two together, and then this is going to be our input and Q is going to be our output. Okay, so hope that's clear. We have clear and preset tied high, so they're not going to do anything. D is always not Q, and we're going to input our clock and we're going to output it. So we're going to wire this over on the board here. I already have it wired, so let's move over there. Let's see if I can do this without upsetting too many things. Tripod is catching on things. Alright, so here is our circuit. This is a 7474. We have power applied to it. We have it wired up like we have there. We are running the input of the clock input. We're bringing that in from our signal here, which is our PC increment. So we're bringing PC increment in, and we are displaying PC increment on this LED. So you can see that it's mostly high, and once in a while it pulses low. So that's our increment. So I have the clock going very, very slow. So every 16 counts it goes low, right? Because that's the state machine. And then I have that clock going into the flip-flop, and then I have it coming out on this LED. So you can see when this flashes low, when it comes back high, it then updates the Q output. So you can see every time this is changing state. Every positive edge, it's changing state. So that would say there's no double pulse. So this particular circuit does not exhibit the double pulse. So it's not counting by 2, it's only counting by 1. So for some reason, our PC counter, our program counter, which is using 74LS163 chips, is for some reason double pulsing. So there may be an error on the PC board, there may be an error in the way its logic's working, it may be damaged. but it's exhibiting a completely different symptom than what we have here on the breadboard. The breadboard is acting completely perfect. In fact, if we take the signal that we get out of the flip-flop, it's divided by 2. We've cleaned it up. And we run that over to our program counter. I don't know if you saw that. Maybe I can move over a bit so you can see it better. If you watch the program counter, you can see it count by 1, and it's not doing a double count. There. It didn't do a double count, and that's because we were dividing it by 2. Now, if I take the program counter, and instead of running it through the D latch, I will run it directly off of PC increment, and we'll watch and see if we get a double pulse. Flash, flash. So still not sure why this circuit over here doesn't double pulse, and this one does double pulse. So I think what we've done is we've at least pointed at this circuit being the culprit. I believe that our state machine is outputting clean pulses, and if you had a circuit that could accept those clean pulses, it works just fine. If you clean up the pulse, divide it by 2, it works great. So this thing seems to operate with it divided by 2. So what's the difference? It's slower. I don't think that's the problem. It is a square wave instead of a non-symmetric square wave, right? The normal signal is 15 counts high, 1 count low. 15 counts high, 1 count low. Maybe it doesn't like that. Maybe it likes a square wave instead. So let's speed this thing up. I'm changing the clock speed. So now we have the PC increment going quite fast, but when we divide it by 2, we can see it pulse. So now let's take a look at the counter here. And I don't know if that's counting right. That doesn't look right to me. Let's see if we can. Yeah, I'm not sure. Let's see here. Oh, we don't have the. We have it. I'm still using the PC increments. That's why it's still double pulsing. So let me put it to the output. Excuse me. Okay, there we go. So now we're running it on the output, which is the square wave now. And we can see that it is counting perfectly fine, even at a higher rate. Let's make the rate even higher than that. And now it's too fast for me to see what's going on. I suppose we could put a oscilloscope to see if it's counting correctly, but I believe it is. So, for whatever reason, this likes square waves and doesn't like the asymmetric wave. So that is interesting. I think we should try to see if there's something funny with the LS163s, or if there's something funny with the way the PC board is laid out. But anyway, a clue, which is great, because we've eliminated any glitches. There were some comments about maybe a glitch being seen on the logic analyzer. These cheap logic analyzers, these I don't know how to pronounce it, Saleae, Saleae. They're really, really cheap logic analyzers, and they glitch all the time. If you look at them, you'll get these spurious pulses every once in a while. They're just a cheap thing. And they're also, if you had a real logic analyzer, I could actually capture glitches and stuff too. You can set them up to monitor glitches and count pulse and things like that. These cheap little analyzers are great for most of the things, but they do have their limitations. And one of the limitations is they do give spurious pulses. So don't be tricked into thinking that this really is seeing what it's seeing. I did put my oscilloscope on the signals, and I didn't see anything. So I was pretty convinced that the signals were clean. But this is a great way to do it. If you really think there's something wrong, go ahead and build yourself a little circuit to do a particular task. The task for this one was to count pulses. Every pulse should have given us a count on the LED, and we can see that it's dividing it by 2 just fine. No glitches. It's not doing a double pulse. Everything looks great. And now we get a clean pulse over here. So, what is the next step? The next step, like I said, I think we need to take a look at the circuit. Maybe we can take this PC counter to a function generator and try to duplicate a high pulse with a short low pulse, and see if it doesn't like the asymmetric waveform. Maybe that's the trouble. I don't know why that would be. It seems like an edge is an edge, doesn't matter what the state in between is. Although the data sheet does show it with a square wave clock input, which is very unusual. Again, it seems like every time we look at one single component, the components always check out okay. But when we put them together, they don't work quite right. But definitely want to look at the circuit. I think maybe another thing to do. Oh, I can't. The old program counter didn't have an ability to put a monitor on it. It didn't have the LEDs. What I might do is build up a second one. Maybe this one got plugged in backwards at one time, and maybe there's just something funny going on with this particular one. So a nice thing to do, if you ever have the luxury, if you have 2 of something, you can always swap them in and out and see if they behave the same. So I think maybe building a second program counter and putting it in and see if it behaves exactly the same way is an interesting thought experiment. And the other one to do is to try to simulate a non-symmetric pulse going into this thing and see if that can duplicate it as well.